Check one. Check one. Check one. Right. Good evening, everybody. Today, we are going to do a question discussion session on your mixtures lesson. That is your grade 11 unit number 3. We are going to do past paper question discussions today. Already have sent the tute to you and I told in the class, try the questions and keep so that we can do the discussion. That's the plan for today. Before we start, confirm me from your end. Can you all see me clearly and hear the sound clearly? Is video, audio, everything clear? Yes. 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 Hurry, right. I have allowed the unmute feature for y'all. See that y'all keep an eye on the microphone as well, right? Those who can talk with me, you can unmute and talk with me regarding the section I am discussing. Hurry, right. We'll start the session without any delay. I already sent the tute to you classifying all the essay type mixtures questions. All the essay type mixtures question from 2024 O level to 2018 O level. Not hard now. Those who have tried it already, you would have understood. Mixtures lesson, even though we talk so many deep things, but the questions that they are asking is very simple, direct question, right? I hope already you have done. I told you to do it because this is a discussion session. I won't give time for you to separately do now. I told already do this, and here we are going to discuss. So if there are any wrong answers or if there are any additional notes that you want to write, you can write in a separate paper or a separate book or something. However, there will be some extra notes, no? That is why this question discussion is very important. Guaranteed there will be some extra things other than the theory things. Because I have already been telling this in the class also. Your final O-level paper is not fully your textbook. Just by studying your textbook and going to the exam, don't believe that you can get the full scope. You have to do papers. Paper theory is little bit different, little bit different to your textbook theory, right? So here there will be some techniques I'll be teaching, repeated type questions I will be teaching. So those things either you'll write in a separate book or separate paper. And already we have the mixture tute. Now you can put it in the mixture tute and keep it separately. Hey, now quickly run and get some separate papers or a separate book and send me ready. Get with the things that you need to write additional notes and send me ready. Yes. Ready. Yes. 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 Hurry. Hurry. We'll start. Take your 2024 O-level paper. 2024. That is your first question. 2024 O-level paper. Right. Shown by the figures below are 5 sets of apparatus that can be used to separate the components of a mixture. Now, when they talk about this, you should understand what section they are talking about. What section they are talking about? They are talking about separation techniques. They are talking about separation technique. Quick revision, very quick. Very quick revision on separation techniques. Very quick revision on separation techniques. What are the separation techniques we have? One, mechanical separation. Mechanical separation. In mechanical separation, how do we separate the component? Now, while I'm telling, see that you also tell with me. These things we have already done in the theory class. Now we are going to revise that. In mechanical separation, what type of separation method we are using there? We separate the components of a mixture using their differences in the physical properties. We separate the components of a mixture using the differences in their physical properties. Physical properties means particle size, particle shape, the density, magnetic properties, electrical properties. Using those properties, you do the separation, that is mechanical separation. Next, evaporation. Evaporation or vaporization. Evaporation or vaporization. Tell me an application where you use evaporation or vaporization, especially in industries.
In the production of salt.
Salt production. When you hear the word evaporation, vaporization, what should come into your mind first is salt production. Next, filtration. Filtration. In filtration, what you do? In filtration, what you do? In filtration, Lamai, first of all, you should have a filter. You should have a filter. You should have a filter. Filter is the device used for the filtration. Tell me some examples for filters. Examples for filters. Filter paper, coconut milk stain. Those are all filters. Sand filters are there. So filter paper in your syllabus, what is there is in your books, what is there is filter paper, coconut milk stain or milk stain. Those are all filters. That's the device we use. And we add the mixture into this. The solution that comes down, the solution that comes down from this is called as the solution that get filtered is called as
Filtrate.
Filtrate. And the substance that remains on the filter, the substance that remains on the filter is called as the
Residue.
right. So that is filtration. Next, crystallization. 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 Crystallization is also it's also evaporation, vaporization. In evaporation, vaporization, what you focus is the vapor part of it. In crystallization, what you focus is the crystal that is formed. So in salt production, actually, two separation techniques are involved. One, evaporation and crystallization. Salt production is a method that is used to separate salt using evaporation and crystallization method. Both evaporation and crystallization are involved. But for you to do crystallization, first of all, there should be a component in the mixture that can turn into a crystal. Again, for you to do crystallization, first of all, there should be a component in the mixture that can be turned into a crystal. There should be a component that can turn into a crystal in the mixture. Otherwise, you can't do crystallization. Now, for example, sea water. Sea water has salt which can turn into a crystal. So when you heat it, water will vaporize, salt crystals will be formed. So there is a component that can become a crystal there. But you all tell me, hydrochloric acid and water. Hydrochloric acid and water. Can you do crystallization there?
No.
A mixture of hydrochloric acid and water.
Can't.
Can you do crystallization there?
No.
Is there any component in it that can turn you into a crystal?
No.
In hydrochloric acid and water? HCl plus water? Is there anything that can become a crystal there?
No.
No, sir.
Can I do crystallization to hydrochloric acid and water?
Can't.
So remember, there should be a substance that can turn into a crystal. Crystallization. Next, recrystallization. Recrystallization. I'm telling and going at a short note again, you can write and give. Recrystallization. Where you do recrystallization? when you want to get pure crystals from impure crystal. When you want to get pure crystals from impure crystal. Pure crystals from impure crystal. From impure crystal. Pure crystals from impure crystals are obtained by recrystallization method. Pure crystals from impure crystals by recrystallization. By recrystallization. Next, solvent extraction. Next, solvent extraction. Solvent extraction. Solvent extraction. Solvent extraction. When do you do solvent extraction? When there is a component that is almost or slightly miscible in one solvent, but it is greatly miscible in another solvent. When you have a component that is slightly miscible in one solvent, but greatly miscible in another solvent, then you do solvent extraction. Now, for example, if you take iodine is slightly miscible in water. That means it doesn't actually dissolve well in water, but it can mix well in organic solvents. It can mix well in organic solvent. Someone is asking what is miscible? Miscible means mixable. Mixable is miscible. Iodine is very slightly miscible in water. It almost doesn't dissolve well in water, but it can dissolve very well in organic solvents like carbon tetrachloride, cyclohexane. It is very well miscible. So when iodine is immiscible in water, slightly miscible in water, but very well miscible in organic solvent, what you do, you keep the solvents together, then iodine get extracted into the organic solvent. Iodine doesn't dissolve well in water, but it can dissolve well in organic solvent. So when you keep them together, guaranteed iodine will leave the water, it will go to organic solvent. Can you remember the biryani example I told in the class? You don't like red rice, but you like biryani. So when red rice and biryani are given as the option, you won't eat red rice, you will go for biryani. Iodine doesn't like water, iodine like organic solvent. So when water and organic solvent are given as option, iodine will leave the water and go to organic solvent. That is solvent extraction. I'm explaining very simply. Solvent extraction. Next, distillation. In distillation, we have three types of distillation: simple distillation, fractional distillation, and steam distillation. Steam distillation. What you do in this distillation process? By supplying heat, you vaporize the component in the mixture. Then by cooling it, you condense that component and take it. You boil, you heat it, you boil and vaporize a component, then you cool it, condense it. So both boiling and condensing are involved in distillation. By supplying heat, you boil and vaporize a component, then you cool it and condense that component. So both boiling and condensing are involved in it. Usually for condensing, we have to use a device. Tell me a device that can be used for condensing in a lab.
Liebig condenser.
Liebig condenser.
Liebig condenser. First go into simple distillation. When is simple distillation done? When there is one volatile component in the mixture. When there is one volatile component in the mixture, you do simple distillation. What is volatile component? What is volatile component?
Evaporation component.
Your line is not 100% clear, Puta. Can you repeat?
Which can be evaporated by heating.
a component that can be evaporated. A component that can be vaporized is a volatile component. Petrol is very highly volatile. It will easily vaporize. Thinner that we put to the varnish, that is highly volatile. It can vaporize easily. Water, when you supply heat, it can vaporize. It's a volatile component. But what about rocks? Are they volatile?
No.
Rocks.
No.
Diamond, is it volatile? Can it vaporize?
No. No.
Glass, is it volatile? Can it vaporize?
No.
Things that can vaporize by supplying heat is volatile. Things that can't vaporize by supplying heat is non-volatile. So here you do simple distillation when there is one volatile component in the mixture that has to be separated. For example, you take well water. In well water, there is a mixture of different components. Tell me, what are the components present in well water? Water. What else? Dissolved gases, dust,
Yes.
maybe some plant materials, maybe there, minerals are there, salts are there, guppy fish is there.
Some microorganisms.
Microorganisms are there, but we can't consider that as a separate component. So those are different components in well water. Out of them, only one volatile component is there. What is a volatile component in well water?
Water.
Water.
Dust can't
Water, yeah.
vaporize. Guppy fish can't vaporize. Aquatic plants can't vaporize. Minerals can't vaporize. Salt can't vaporize. Only one volatile component is there. So if you want to obtain pure water from well water, pure water, what's the correct term for pure water? Scientifically, what we call pure water?
Distilled water.
Distilled water.
If you want to obtain distilled water from
Distilled
well
water.
water, you can do simple distillation. So if you want to obtain distilled water from well water, you can do simple distillation. If you want distilled water from well water, you can do simple distillation. Next, coming into fractional distillation. When is fractional distillation done? When there are more than one volatile component in a mixture that has to be separated. When there is more than one volatile component, when there is two or more volatile components, you do fractional distillation. So remember, one volatile component, simple distillation, more than one volatile component, fractional distillation. Tell me the best example where fractional distillation is done.
Extraction of crude oil.
Crude oil.
Extraction
of components in crude oil. Probably tell that. Extraction of components in crude oil. Extraction of components in crude oil. Crude oil is mineral oil. Tell me some components in crude oil. What is there in crude oil?
Petrol,
Kerosene.
diesel.
liquid
Kerosene.
petroleum gas,
Gas.
petrol, diesel, tha.
Diesel, super diesel.
Yeah, LP gas is
Jet
there.
fuel.
Petrol is there. Kerosene is there. Diesel is there.
Lubricated materials.
Naphtha is there. Inca oil is there. So those are all different volatile components in the crude oil. If you want to obtain petrol separately, you do fractional distillation. If you want to obtain diesel separately, you do fractional distillation. So when you need separate components there, you do fractional distillation. And after the distillation, what is going to remain there?
Tar.
Tar.
Tar will be remaining. And for fractional distillation, we use a special setup. What is that setup
The
called?
fractional column.
Fractional tower.
Fractionating column.
Fractionating column or fractionating tower also correct. Fractionating column has to be used. Out of simple distillation and fractional distillation, where you need to supply, where you need to control conditions, where you need to do control conditions, especially controlling
fractional
temperature.
Fractional
In fractional distillation, you have to go with control condition. Simple distillation, you don't need any big control condition, but here you need control condition. Steam distillation. When is steam distillation done? When the volatile component is present inside a plant material. When the volatile component is present inside a plant material, you do steam distillation. For example, cinnamon oil is present inside the cinnamon leaf. Cinnamon oil is present inside the cinnamon leaf. So if you need cinnamon oil from the cinnamon leaf, you do steam distillation. So remember, steam distillation is done when the volatile component is present inside the plant material. Inside plant only, here the volatile component. So all these three go as volatile. Simple distillation when there is one volatile component. Fractional distillation when there is more than one volatile component. Steam distillation when the volatile component is present inside plant materials. Mainly, this is done to obtain essential oils. Mainly, this is done for essential oil. Cinnamon oil, cardamom oil, nutmeg oil, eucalyptus oil, lemongrass oil. All of them essential oil steam distillation is done. Finally, chromatography. Let me remember, chromatography is a method used to separate and identify. It's a separation and identification technique. Can you separate and take the component out? No. In all the other separation methods, you can separate and take the component out. Evaporation, you can take the salt out. Filtration, you can take the filtrate out. Crystallization, you can take the crystals out. Recrystallization, you can take the pure crystal out. Solvent extraction, you can take iodine out. Simple distillation, you can take distilled water out. Fractional distillation, petrol, diesel, all of that you can take the out. Steam distillation, you can take essential oil out. In all the others, you can take the component out. But in chromatography, you can't take the component out. You can't take it out. It's a method used to separate and identify only. Only separation and identification is done in chromatography. As this is online, I can show you all a simple video on chromatography. In the interactive class, in the online session, I think I show. Is chromatography. They are doing chromatography for chlorophyll. Right. Again, watch. I will explain them now. First, you take the leaf that you need to obtain chlorophyll from. Usually, we use spinach leaf. We take the spinach leaf and you grind it. Put some solvent like acetone and grind it. And then extract the chlorophyll. See, they are taking the chlorophyll. Take some chlorophyll. Keep some drops of chlorophyll in. What is this paper?
Chromatography.
Chromatography
Chromatography.
It can be a chromatography paper. It can be a filter paper. Even you can use a A4 paper. But best is chromatography paper. Second best is filter paper. You cut it in a stripe-like shape. You keep some chlorophyll extract at the bottom. At one edge, you keep the chlorophyll extract. That is what we are going to do chromatography on. Then you add some solvent into a separate test tube. Now here they are using a measuring cylinder. Usually we use a test tube or a boiling tube. You put some solvent there. For chlorophyll chromatography, what solvent can be used?
Water.
Not water, not water. What is the solvent for chlorophyll chromatography?
Alcohol.
Acetone.
Acetone.
Acetone, petrol,
one
kerosene.
option. Yes, good.
Petrol,
Petrol, very good.
kerosene,
Alcohol.
Very good. Petrol, acetone, or you can use kerosene. Those are the solvents that we use for chlorophyll chromatography. This petrol, acetone, or kerosene, the solvent that we are using, is given a common name. What's the name given to that?
Mobile phase.
Mobile phase. Very good. The solvent that we are using is the mobile phase. The solvent is the mobile phase. So they are adding that. They are adding that. And then the paper is added in. The paper is given another name. What is the name given to the paper?
Stationary phase.
It's the stationary phase. So there are two phases in chromatography, mobile phase and stationary phase. Mobile phase is the solvent that we use. Stationary phase is the paper that we are using in paper chromatography. Only paper chromatography is there for you. So when you put it inside, what will happen? Solvent will rise up. Together with the solvent, the components in chlorophyll will also rise up. But different components will travel different lengths. Together with the solvent, the components in chlorophyll will also rise up, but different components rise up in different levels. Different components travel different lengths. All the components cannot travel same length. See, here different components are traveling different lengths. So after that, you can take and find out what are the components there. So here they have given the components. So this is a separation and identification test technique. See, I have only identified what are the components. Chlorophyll, A, B, HEMO, what is there? I have identified. Can I take them out? Now, can I take the carotenoid out? Can I take it? Can I take it to a cup or something?
No.
That you can't do. That's what I mean by you can do the separation, but you can't take it out. So it's an identification technique. That's the key word. That's an identification technique.
Sir.
It's the identification technique. Wait, I'll come to the questions. Go tell me, this is done for volatile components or non-volatile components?
Non-volatile.
Non-volatile
Those are simple
components.
points that are there. This is done for non-volatile components. Sorry. Yeah, any question related to this?
Sir, what happens when the filter paper touches the tube?
What happens when the filter paper touches the tube? This is the tube. This is the solvent. This is the paper. It's closed. This is the chlorophyll. You should make sure that paper doesn't touch the tube. The stationary phase doesn't touch the test tube that you are using. Then only nicely the components will rise up. Nicely the components can rise up. Let's take this is touching. By mistakenly you slanted it and it's touching now. From one corner or somewhere it's touching. If it touches, what will happen? A certain amount of petrol will be there in the walls of this boiling tube. That petrol will come in. That petrol will come in. So if that petrol comes in, the upward flow of the components of the chlorophyll will also get interrupted. So chlorophyll component will also go in a slanted path now. Harinila, practically think when this touches the corner, in those corners, won't there be some petrol? Can't the petrol vaporize and can't the petrol vapor be present in those corners? Possibly. So if the paper touches the corner, from corner petrol will come in. So from corner, if the petrol comes in, or whatever the solvent you are using, from the corner, if the solvent comes in, now here we are, let's say you are using petrol or acetone, kerosene, if that comes in, now the upward motion of the components of the chlorophyll get interrupted. It can't go vertically up. It will go in slanted path. Now you will tell, so that doesn't make any big problem. No? Even if it goes slanted path, we can find out the components separately. No? Yes, we can. But after this, we do a separate calculation called RF factor calculation. RF factor calculation. For that RF factor calculation, we need the vertical height of the component. Vertical height. So if the component travels in a slanted path, can we calculate the RF value? No. So that's something advanced for you, RF calculation. So you can't do that. So you should make sure that component travel in a vertical. Hurry. Now we'll go to the questions.
Sir,
Yeah.
why should we close that tube?
To make sure that the test tube is saturated with the solvent you are using. Saturated with the solvent you are using. Now let's take its petrol. Petrol vapor should be present everywhere around this. That is called saturated. It should be present everywhere around. If you open it and keep, petrol will go out. This won't get saturated. This won't have enough petrol in it. So there should be petrol vapor everywhere inside the tube. So you close it and hurry. Shown by the figures below are 5 sets of apparatus that can be used to separate the components of a mixture. Right? We'll identify this. Filter paper is there. Now you will tell, sir, filter paper is there and filtration needed. Yes, filtration possible. Abating heat is given. With filtration, heat is supplied in what separation technique? With filtration, heat is supplied in what separation? Make a filtration manevi. With filtration, where we supply heat
Simple
together.
distillation.
Simple
It's
distillation.
recrystallization. It's recrystallization. Keep that in mind. Can you remember when I was teaching recrystallization, I gave you all a flow chart. In recrystallization, first you dissolve the impure solid, dissolve the impure solid in a hot solvent. Then you filter that. Check that flow chart. After you dissolve, you filter that. After you filter only, you do the crystallization process. So in recrystallization, you have to filter and then you have to filter in the hot solvent. For that, you need to supply the heat. So you filter in the hot solvent and then you do the crystallization. So this is recrystallization. So remember, in recrystallization only you filter as well as supply heat. If it is only filter, then it's filtration. Filter plus heat, recrystallization. Keep those points in the mind. Now, these are important points, and this is why doing papers are important. If it is only filter, it's filtration. If it is filter plus heat, recrystallization. B. What is this device?
Liebig condenser.
That's not Liebig.
Used for solvent extraction.
Separating funnel. Separating funnel.
And
Separating funnel.
I gave those names in the class. This is a separating funnel. That's a separating funnel. Separating funnel is used for what?
Solvent extraction.
Solvent.
Solvent extraction.
This is solvent extraction. Chromatography paper. That comma you should tell. What is this?
Chromatography.
Chromatography. Now you will tell, so sir, for chromatography we should use a boiling tube. No, there is no such rule like that. You don't need to exactly use a boiling tube. Even you can use a beaker and do the same chromatography. You can use a beaker to do that. Doesn't matter. See? This is also correct. You can use a beaker. But actually this is not 100% correct because beaker is not closed. You should put a, what you call, watch glass and close it. So it's also correct. You can do it in a beaker as well. So this is chromatography. You're supplying heat. What is this part?
Simple distillation.
Liebig
condenser.
condenser.
Liebig
Condenser. Where you use Liebig condenser? 3 places. Simple distillation, fractional distillation, steam distillation. Out of that, this can be what?
Steam
Simple
distillation.
distillation.
This is simple.
Distillation.
This is simple distillation. This is what?
Fractional.
Remember, this part is fractionating tower. It's a fractionating tower, fractionating column. A fractionating column is fitted for fractional distillation. Fractional distillation.
So how do
remember
we
the
distinguish?
differences. This is simple distillation. There is no fractionating tower, no fractionating column. Here, this is fractional distillation. There is a fractionating tower. This picture, keep in mind. If this picture comes, guaranteed fractional distillation. If this part is not there, simple distillation. If this comes, fractional distillation. If this part is not there, it is simple distillation. එතකොට this setup. I'll just draw it rough.
Steam distillation.
This kind of a setup.
Steam distillation.
Steam distillation.
Steam
This is
distillation.
steam distillation. This is steam distillation. This kind of a setup is steam distillation. So remember the setups for the distillation. Two volume round bottom flask like this with the Liebig condenser is steam distillation. This setup, fractionating column is there on fractional distillation. No fractionating column, na simple distillation. Hurry, we'll go to the questions. Simple question, but when we discuss, we can discuss so many things. Problem 1, identify the set of apparatus that can be used for each of the following need of separation and write the letter that corresponding to that. The same letter can be used more than once as well. A, obtaining pure crystal. Lamai, no need to read anything else. The moment you see pure crystal, only one answer. What is that? Pre-crystallization.
Crystallization.
Repeat with me. The moment you see pure crystal, what should come into your mind?
Recrystallization.
Everyone? Well, the moment you see pure crystal, what's the answer? Recrystallization. Who tells me it is recrystallization here? A. A is recrystallization.
A.
Second one. Identifying the pigments. Lamai, the moment you see the word identifying, only one separation technique. Those are keywords.
Chromatography.
Chromatography.
No need to read anything else. If you want, you read. I am lazy to read. The moment you see it's chromatography, answer C. Identification. Keywords I am underlining here. The moment you say identify, it's chromatography. See, extracting iodine. The word extracting, and if you see iodine, only one answer. What is that?
Extraction.
Solvent extraction. There is no two stories. If you see the word iodine, if you see the word extraction, guaranteed it is solvent extraction. See, correct? No? Extracting iodine dissolved in water into liquid cyclohexane, which is immiscible with water. Anything solvent extraction. Which is solvent extraction? B. For that, you should know this setup. This is separating funnel. Separating funnel is solvent extraction. D. D. Obtaining miscible ethanol, boiling point 78, and acetic acid, boiling point 118, separately from a solution of them. Right.
Fractional distillation.
Fractional distillation.
I'll explain. Wait. The unique wait. Ethanol has a boiling point. Acetic acid also has a boiling point. Both have a boiling point. Now both are volatile. Both can boil. Both can become a vapor. Both can become a vapor. Now both are volatile. Two volatile components are there. Ethanol is a volatile component. It boils at 78. Acetic acid is a volatile component. It boils at 118. So two volatile components. What separation?
Distillation.
Fractional distillation. That is E. Two volatile component, fractional distillation answer E. Last one, separating the components of chlorophyll.
Chromatography.
Chromatography.
They are told you can use same letter more than once. That is C. Just correcting answers is not enough. Whatever the additional reviews you have, write and keep. Hurry. With that, we'll do the last question as well. 2018. This 2018. First one done. Now I'm going to the fifth one. This is fifth one. Given in the box below are several techniques used to separate components in mixture. Right? Okay. Sifting, filtration, crystallization, recrystallization, blah, blah things are there. Write separately which technique given in the above box is most suitable to fulfill the requirements Roman 1, 2, 3, 4 given in the first column of the following table. Right. Roman 1. Obtaining PO potassium chloride. The moment you see PO, what's the separation technique?
Recrystallization.
Crystallization.
Nothing else.
Crystallization.
I'll just write it here. Recrystallization. Roman 2. Obtaining most of the iodine. What?
Solvent extraction.
Solvent extraction.
Can you see how that previous question is helpful here? Solvent extraction. Don't need to write anything. If you want, you read. I am lazy to read. Next. Roman 3. Identifying with the first word we know the answer.
Chromatography.
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 Last one. Separating hexane and octane from a mixture formed by mixing the liquid hexane and octane. When you read this one, you might not understand 100%.
Fractional distillation.
This is actually, you need the hydrocarbon knowledge. Wait, I'll explain. You need the hydrocarbon knowledge. If you go there, you can come to a conclusion. Hexane and octane are miscible liquid. Boiling point of octane is higher than the boiling point of hexane. Both have a certain boiling point. Which means they are
Fractional distillation.
Fractional distillation.
first answer me this. That means they are volatile.
Volatile.
Two volatile components, octane and hexane, both are volatile components. What separation?
Fractional
Fractional
distillation.
distillation.
You might have gone this wrong. No problem for now. Because there's another way of getting the answer. I got the answer this way, But to get that answer, you need the hydrocarbon knowledge. When we learn hydrocarbon, you will learn about hexane and octane. Hexane and octane are actually hydrocarbons. Remember, to separate the components in hydrocarbon, we do fractional distillation. It comes later. To separate the components of hydrocarbon, we do fractional distillation. Hexane and octane are hydrocarbon, you can do fractional distillation. But some people with the mind game, you can do this question. Octane QM, what comes into your mind?
Octane 92.
Fractional distillation.
Where are you use the
Petrol.
octane word? 92
Petrol,
octane, 92
petrol.
octane.
Chromatography.
Petrol.
Solvent extraction.
Petrol QM, what's the separation technique you should be using? Fractional distillation. Petrol is crude oil. Hot. 2 questions done. We'll do the calculation question. I'll keep that question for a minute in case if you want to write. Right. We'll do a calculation question. This one. What about second question? Second question, no calculation. I'll come to the second question. We'll do the third one. Calculation. And then I'll go to the second one. First and the fifth are done. 1 and 5 are done. Now we are going to do the third one. For a laboratory experiment, a student prepared 500 centimeter cube of sodium hydroxide. This is the volume. Sodium hydroxide solution with concentration 1 mole per decimeter cube. I personally, if I am doing these types of questions, what I do is, those important data, I write separately in my answer sheet and keep. They are telling the volume 500 centimeter cube. Concentration 1 mole per decimeter cube. What is the chemical they are talking about? What is the compound they are talking about? Sodium hydroxide. These data I will write separately and keep. Question E. Name 2 laboratory glasswares required to prepare the above solution. Right. What we need to prepare standard solution? What are the equipment we use to prepare standard solution?
Wash bottle.
To prepare standard solution, you need a watch glass. I'll write all the materials. Watch glass, wash bottle, wash bottle. You need a funnel, a glass funnel,
Volumetric
and
flask.
a
Volumetric glass.
volumetric
Flask.
flask. Out of these, only two they are asking. Again, repeat with me. Again, repeat with me. This is a repeated type of question. Eh? What are the glasswares that you? What are the materials that you need, or glasswares that you need to prepare a standard solution? Watch glass,
Watch glass.
bottle,
Wash bottle. Funnel. Volumetric flask.
They are asking glasswares or materials. Me lamai me
Glasswares.
glasswares. Etokota, can you write wash bottle?
No.
Can't.
No. Wash glass.
Wash bottle you can't
No.
write there because wash bottle is not glass. If there's only glassware, you write watch glass, funnel, volumetric flask. These are the glasswares. If they directly ask the materials that are needed, you include wash bottle as well. So I will write like this and cut it and so this you write if they ask the materials. If they are the glasswares, only these three you can write because those three are the glasswares. Out of these three, you can write any two. Roman 2. B part. How much is the mass of sodium hydroxide? Mass of sodium hydroxide required to prepare the above solution. The relative atomic masses are given: sodium 23, oxygen 16, and hydrogen 1. Right. And what are the details given to us? Concentration is given, volume is given, C given, V given. What are they asking? They are asking the mass of sodium hydroxide. C given, V given, M they are asking. Y'all tell me, do we have any relationship between concentration, volume, and mass? Do we have any direct relationship between concentration, volume, and mass? Do we have any equation?
No.
No, sir.
No.
No, sir.
No.
No, sir.
No. No equation, no direct relationship between concentration, volume, and mass. What kind of equation we have for concentration? We have the
C
equation
equal
Concentration equals N over V.
V. Concentration is equal to number of moles of volume. That is the equation we have. Now, what is given? Concentration given. Volume given. Number of moles not given. That means using concentration equal number of moles over volume equation, I can find number of moles. Why? C is there, V is there means I can find N. I can find number of moles. Y'all tell me, if I know the number of moles, can't I find the mass?
Yeah.
Yes.
can.
How to find mass using number of moles? What's the equation for that?
N equal
N equals M over M.
Number of moles equal mass over
over
molar.
capital M.
So from the first equation, we can find number of moles. So now we know the number of moles. Molar mass you can calculate. No, sodium hydroxide, NaOH, you can calculate the molar mass. From there, you can find the mass. So you do the question in two steps. First, using C equal N over V, you find N. Then using N equal M over M, you find M. We'll start. C equal N over V. Is concentration given? Yes. What's the
Yes.
concentration? 1 mole per decimeter
mole
cube.
per
decimeter
Concentration is 1 mole per decimeter cube. This is where students make mistake. Okay? Listen. That is equal to number of moles is given divided by panna. Don't go and write directly. Volume is 500 centimeter cube. Lamai. Volume is given in centimeter cube. Concentration is given in decimeter cube. Ehnang, can you directly write 500 centimeter cube there?
No.
No.
No, sir.
You can't write different units in the same equation. In a single equation, all the units of the physical quantities should be same. You can't write volume in centimeter cube and concentration in decimeter cube. So my job is I need to convert centimeter cube to decimeter cube. I need to convert centimeter cube to decimeter cube. How to convert centimeter cube to decimeter cube?
Divide by
Divide by 1,000.
Divide by 1,000.
What I have told you, memorize this. Centimeter cube is like grams. Decimeter cube is like kilograms.
Kilogram.
How to convert grams to kilograms? That is scholarship. Gram to kilogram.
Divide by
Divided
1000.
by 1000. Gram to kilogram, you divide by 1000. Same here. Centimeter cube to decimeter cube, you divide by 1000. Harinne lamai? 5000 gram. How many kilogram? 5 kilogram. What to do?
5
Divide.
kilograms.
5 kilogram.
Reverse also tell me. Reverse also tell me. How to convert kilogram to grams?
Multiply by 1000.
Same logic here. Decimeter cube to centimeter cube, you multiply by 1000. Ehenang, what's the centimeter cube given here? 500 centimeter
500.
cube. Go tell me. 500 centimeter cube. How many decimeter cube? 500 grams. How many kilograms?
0.5 decimeter.
0.5.
0.5 kilograms. That is 0.5 decimeter cube. Right. So now we know the volume in decimeter cube. That is 0.5 decimeter cube. So if I substitute that value there, volume is 0.5 decimeter cube. If I need to find number of moles, I should subject number of moles. If I subject number of moles, denominator, this goes to the other side. Division on the other side become
Multiplication.
multiplication. So number of moles is equal to 1 mole per decimeter cube multiplied by 0.5 decimeter cube. If I do the math there, 1 into 0.5, how much?
0.5 mole.
0.5. Units, dm to the power plus
Mole.
3, dm to the power minus 3 cancel off. When
Mole.
those two cancel off, what is remaining?
Mole.
Moles are.
Mole.
Is that the final answer? Are they asking moles?
No.
They're asking mass. So now we know number of moles. Now we need to find the mass. How to find the mass? Your second equation. Number of moles is equal to mass over molar mass. But to
Molar mass.
apply this equation, first you need the molar mass of sodium hydroxide. We'll find the molar mass of sodium hydroxide. Some students have a bad habit. What's the bad habit? You do the molar mass calculation separately somewhere. Separately behind the book or separately in your rough sheet. Don't do it. Do the molar mass calculation in your answer sheet itself. Wherever you are writing the answer, there itself do the molar mass calculation. Right. Molar mass of sodium hydroxide. Relative atomic masses are given that you don't need to memorize. But if you have memorized it, it will save a lot of time. Sodium 23, oxygen 16, hydrogen 1. Sodium 23, 1 sodium is the oxygen 16, 1 oxygen is the hydrogen 1. Altogether how much? 40 grams.
40 grams.
I will write the values. Number of moles I have 0.5 mole. Mass I don't have, that is what I am calculating. Divided by molar mass I have 40 gram per mole. If I need to find mass, I need to subject mass. If I subject mass, 40 goes to the other side. Division on other side become multiplication.
Multiplication.
So mass is equal to 0.5 mole multiplied by 40 gram per mole. That is half of 40 is 20 grams. Praise than those who got this. Now, like this, we have done a lot of questions in the class. Hundreds of, no, 100, at least about 30, 40 questions we have done. Right. In case if you have not got, quickly write it. I'll give 1 minute. Okay. You're still writing, take a screenshot. See what? It was experimentally found out that the concentration of the solution prepared by the student was a little less than 1 mole per decimeter cube. Practically, this happens, Lamai. Now, these are practically done in the lab. Even though your aim is to prepare 1 mole per decimeter cube concentration, when you are practically doing this, there may be some mistakes, there may be some errors. So you won't exactly get 1 mole per decimeter cube concentration. State 2 errors that would have happened in the preparation of the solution causing that defect. What are the errors you can make when you are preparing a standard solution? Now in the class I taught you what are the errors you should not do. What are the places where you should be careful on. Now you make it as an error and tell. What are the errors you can make? Number 1. Not
Improper
weighing
measurement.
the solute accurately. Now here if I properly tell, not weighing the sodium hydroxide accurately. Now we know we need 20 grams of sodium hydroxide by calculation. If you don't weigh it accurately, concentration won't be accurate. So not weighing sodium hydroxide accurately. Number 2, making errors in adjusting the final volume. Making errors in adjusting the final volume. Final volume is 500 centimeter cube. If you don't exactly get it 500 centimeter cube, it will make a mistake in the concentration. Not adjusting the final volume final volume accurately. Number 3, entry of impurities. Not using standard mixing techniques.
Using incorrect techniques for mixing.
Using the
that's
wash
all.
bottle properly.
Also, all those things are included in this thing. No? Not using mixing techniques
Not
properly,
having
entry of any
clean,
impurities
It
into
didn't
the
dissolve
solution.
properly.
Solute not being dissolved properly. So how many they are asking? They are asking only 2. If you have not written, write these 2.
Sir,
Write down.
can you show me the answer for the second one, please?
Okay. Meanwhile, I'll tell the answer for the C1. If you have not written, write these 2. Not measuring the mass of sodium hydroxide accurately. Not measuring the mass of sodium hydroxide accurately. Not measuring the mass of sodium hydroxide accurately. Second one, errors in adjusting the final volume. Errors in adjusting the final volume. Errors in adjusting the final volume. For 3 questions done. Another calculation question is there. It's on. This superb one, 2019 O level. This is a good question, eh? My paper, 2019. A bottle contains 500 centimeter cube of an acetic acid solution. The density of the solution is 1.04 gram per cubic centimeter. And the mass of acetic acid contained in the solution is 26 grams. Before going to the question, I will write this data separately. A bottle contains 500 centimeter cube of acetic acid solution. Right. Acetic acid solution. They are talking about acetic acid solution. Tamai, how a acetic acid solution is made? You take acetic acid and mix it with water. That is how acetic acid solution is made. So we don't know this, no? Yeah, this is not taught in the class. It is expected for you to know this. How do we expect you to know this? I know that you know Salt solution contains salt and water. Don't you know that? Salt solution is salt and water. Glucose solution. What is there in glucose solution?
Glucose and water.
Glucose plus water.
Sugar solution. What is there in sugar solution?
Sugar plus
and
water.
Sugar
Sugar
plus
plus
water.
Sugar plus water. Hydrochloric acid solution. What is there in hydrochloric acid solution?
Hydrochloric acid plus water.
Sodium hydroxide solution. What is there in sodium hydroxide solution?
Sodium
Sodium
hydroxide.
hydroxide plus water.
You know all those 5 things. Ehenang tell me acetic acid solution. What is there?
Acetic acid and water.
Acetic acid plus water.
Now don't tell me you don't know this. Right? You already know 5 of that. So this you know. That thinking pattern you should have in your exam. What is taught in the class, what is asked in the exam. That bridge you should suddenly build. Now some students come and talk to us, sir, I studied everything in the textbook. I studied everything in the Tute. I have memorized everything, but my marks is not building up. Why? You are trying to answer the exam paper exactly the same way you studied. You are expecting the questions exactly the same way you studied. No, they won't give you. Those who make the papers are naughty people. They won't give you exact same words that are in your textbook. If so, everyone will get the best marks. No, they don't like that. So they will play with that. So it's your job in the exam hall to build the bridge between what you studied and what they have asked. That is a skill. You have to develop that skill. It's not a born talent. Don't think you're born with that talent. No, it's a skill that you need to develop. At the exam hall, during that timing, with that pressure, when you read a question, your mind should build that bridge. This is what I studied. This is what they have asked. This is the connection. How do you get that? By doing papers. Just studying, going and doing the final exam. No, it won't do anything. At home, you sit and do many papers. Now start doing. Now we have already started second term in our classes, except Goal. Goal soon will be starting second term. All the other places, we have already started the second term. So now you can do papers. That means out of your full O-level syllabus, 1.5 year is almost over. 1.5 year is almost over. So out of the full O-level paper, you can at least do it up to about 75% of the paper. So you can do papers now. Do papers as much as possible. The more you do papers, the more you will be able to think that bridge. The more you are able to think on that bridge, the more your marks will improve. That is the skill of doing a paper. It's not just studying. So sit, do papers as much as possible. You should study. Now keeping all the studies aside and doing only papers also won't work. First you finish the theories. If you forget the theory, revise it a little bit, then do the papers. Let's say already grade 10, nothing you have studied. If you do the papers, you will give up. That will also happen. I don't know anything. I can't think of anything. I'm going to give up. First you study everything in grade 10. Maximum how many days it will take? Honestly tell me. To complete the full grade 10 book. If you do your maximum. Quote me your days. I will work with you. You give me the best number of days you will take to complete 20 lessons. How many days? Quote me your days. I will quote the longest day. 20 days. I will start with 20-day count. You quote me your days.
30?
15 days at least.
1 month.
1 month.
Perfect. Most of you are telling 15 to 30 days. So in 1 month, can't you finish full grade 10? Actually, I quoted the longest day, 20 days. If you give your maximum, per day, 24 hours are there, 12 hours for Karana, I think you can finish it in 1.5 weeks. I'm talking about studying only, learning the theory only, theory. Not doing papers, nothing, finish the theory. Within let's say your longest day, 30 days is the longest count. 30 days, you finish. After that, don't you have the time to do papers? Still don't waste your time telling, I don't have time. I can't do this, I can't do papers. You do that. First, the days that you quoted, finish your grade 10 syllabus. Grade 11 first term is already over. Finish the first term syllabus theory part first, then touch the papers. I don't think you will have 100% of the theory to study. Already for your school term test, you have studied some things, no? A part sticker will become revision for you, no? So in grade 10, most of the sections are revision. Grade 11 only, they are studying part. So it won't take that much of these. Finish it. Don't keep it. Hurry, right. So acetic acid solution contain acetic acid and water. Acetic acid and water is acetic acid solution. Acetic acid solution. Just like what you told, glucose solution is glucose and water. Sugar solution is sugar and water. So acetic acid solution is acetic acid and water. Now, what are the details they have given? A bottle contains 500 centimeter cube of acetic acid solution. See, for what they have given the data, that is what is important. Reading the question is very important. 500 centimeter cube of acetic acid solution. So this 500 centimeter cube is the volume of the solution. For solution, they have given a data. Solution's volume is given 500 centimeter cube. I'll write it separately. Right. What else they have given? What else they have given? Density of the solution. Another data they have given about solution. Density of the solution is 1.04 gram per centimeter cube. Right. Density of solution is given. Density of solution is given. Density of the solution is 1.04 gram per centimeter cube. Right. What else? And the mass of acetic acid. Is it the solution? No. Mass of acetic acid contained in the solution is 26 gram. Ehenam tell me that 26 gram is the mass of solution, the mass of acetic acid. Read the grammar properly. And mass of acetic acid contained in the solution is 26. That is what
Acetic acid.
grammatically, if you look at the sentence, and mass of acetic acid contained in the solution is 26 gram. So that 26 gram is the mass of acetic acid. So acetic acid's mass is given 26 gram. Acetic acid's mass is given 26 gram. This is called extracting data. This you have to do. This you have to do. Some students, when they read itself, they can extract it in the brain, in the mind itself, this map will come. For some people, you have to draw like this. Eka, you start doing. These things will come if you do papers. With practice only, this will come. Hurry. Now go to the question. Roman 1. Calculate the mass of, read the question properly. Calculate the mass of acetic acid solution. Again, they are talking about solution. Calculate the mass of acetic acid solution contained in the bottle. They are asking the mass of acetic acid solution, not acetic acid. However, they can ask, it's already given. Not water. They are asking the solution's mass. They are asking solution's mass. And look at the data. Volume given, density given, mass is asked. Volume is there, density is there, mass they are asking. Tell me a relationship between density, mass, volume.
Density equal mass over volume.
Density equals mass of volume.
Density plus mass over volume.
Not grade 11, not grade 10. This is grade 9. In grade 9, you all learnt about density. Density is equal to mass divided by
volume.
density, you know, mass you don't know, volume you know. Substitute the values. Density is 1.04 gram per cubic centimeter equal to mass you don't know, volume you know, 500. Now you might ask me, sir, why did you write the volume in centimeter cube? You all tell me, why did I write it in centimeter cube? Should I write it in decimeter cube here?
No, decimeter cube
No
is only
need.
for the concentration.
Density is also given in centimeter cube. Volume is also given in centimeter cube. So no unit changes required. Both are in centimeter cube. So no any unit changes required. So if I subject mass is equal to 1.04 multiplied by 500. Cm to the power plus 3, Cm to the power minus 3 will cancel off. Only grams will remain. So your answer will come in grams. How much? 1.04 into 500. That is 500 plus 20, 520. You jump 2 decibel. Nah, 520 into
20 grams.
yes, 520. Ne?
Yes, sir. 520.
520 grams. That's your answer. Got it now? Most of you have gone wrong. The place where you would have gone wrong is this analysis. What is for what? These are for the solution. This is for the acetic acid. So now I know the mass of solution. Mass of solution is 520 grams. I mean, mass of solution is what? It is the total mass. Neither. Total mass is only 520. Roman 2. Calculate the percentage of acetic acid by mass in the above solution. They are asking the percentage of acetic acid by mass. That means what they are actually asking. They are asking you the mass fraction, mass percentage. Percentage of acetic acid by mass means they are asking the mass percentage. How do you calculate mass percentage? Mass percentage is equal to mass fraction multiplied by
100.
multiplied by 100. Harinella might think mathematically. A percentage is equal to fraction multiplied by 100. So mass percentage is mass fraction multiplied by 100. Volume percentage is volume fraction multiplied by 100. Mole percentage is mole fraction multiplied by 100. So that is mass percentage. Now tell me, what is the mass fraction here? How do you calculate mass fraction? They are asking the mass percentage of acetic acid. Mass percentage of acetic acid. So your mass fraction should be mass fraction of acetic acid. How to write the mass fraction of acetic acid? Mass fraction is equal to mass of acetic acid. Mass of acetic acid divided by total mass. Need mass of acetic acid divided by total mass is mass fraction. That you multiplied by 100%, that is your mass percentage. Mass of acetic acid divided by total mass is your mass fraction. That you multiply by 100, you get the answer. Do we have the mass of acetic acid? Yes, it's already given. 26 grams. Do we have the total mass? Yes, 520 grams.
Yes.
Mass of acetic acid is 26 grams. Total mass is 520 grams. That you multiply by 100, you get the mass percentage. Do the math. How much?
5%.
5%.
0, 0
5%.
cancel out. 26 divided by 52. 26 divided by 52 is half. Half into 10 is 5. Yes, good. 5%. How did it? Not hard. Understanding the concepts is what is important. I'll give 1 minute, quickly write down.
Sir,
Yeah, Bata, go ahead.
so then what is parts per million?
Parts per million. Mass fraction multiplied by million. 1 million is parts per million. Any fraction you multiply by 1 million parts per million. What is now parts per billion?
You multiply the fraction by billion.
A fraction multiplied by billion. So remember, a fraction multiplied by million is parts per million. A fraction multiplied by billion is parts per billion. And of course, a fraction multiplied by 100 is percentage.
Sir, is that density is equal mass over volume?
Yeah.
Okay.
Horine. Still, if you are right, take a screenshot. Right. Okay. Still, I'm getting some doubts. What I will do is at the end, I'll give about 10 minutes. We'll discuss the doubts. First, we'll face the questions, right? Because tomorrow school is also there and I can't drag a lot of time. Right. Roman 3. Vinegar. What is vinegar? What is that? Actually, vinegar, you can make it in two ways. Natural way of making vinegar is there. Artificial way of making vinegar is there. How to make artificial vinegar? You take acetic acid, put water. You take acetic acid and put water. That is artificial vinegar. So basically, this acetic acid solution that they are talking about, is what? Vinegar. Acetic acid solution is vinegar. Vinegar is an aqueous solution which contains 5% acetic acid by mass. Anything here we got 5%. See how nicely they are building this question. Now, when I was doing this question in my ear, I know when I was reading this sentence that my previous answers are correct. If this is correct, only this will be correct. I confirm that this is correct by reading this sentence. They are talking about 5%. Hurry. Vinegar is an aqueous solution which contains about 5% acetic acid by mass. Yes. So actually what they are talking is the previous solution. The boiling point of acetic acid is 118 degrees Celsius. Boiling point of acetic acid is 118 degrees Celsius. What they are trying to tell by that? We'll try to see. Name a technique that can be used to obtain a solution that contains about 10% acetic acid by mass. Already I have 5% acetic acid by mass. Already I have 5% acetic acid by mass. Acetic acid by mass. They wanted to bring it to 10%. That means they wanted to increase the mass percentage of acetic acid there. They want to increase the mass percentage of acetic acid there. In what? In vinegar. Vinegar is what? Acetic acid solution. How acetic acid solution is made? By using acetic acid and water. So basically acetic acid and water is vinegar. So what they are telling, they wanted to bring up 5% acetic acid by mass into 10%. That means they should increase the mass percentage of acetic acid. They want to increase the mass percentage of acetic acid. You all tell me, to increase the mass percentage of acetic acid, what you can do? I ask a very simple question. Let's take your mother is making chicken curry. I don't know how to make chicken curry. So many ingredients are put there. Out of that, chili powder is added. Let's take, she wanted to increase the spiciness of the curry. What you can do? Ask from your mother and tell me. She wanted to increase the spiciness of the curry. What she should do?
Increasing the chili powder.
One method, you put more chili powder into it. Let's take no chili powder at home. Tell me another method.
Heating the curry.
Heating the curry. When you heat the curry, what will happen? The water in the curry will
Evaporate.
evaporate. Water will evaporate. When water evaporates, water content will reduce. When water content reduces also, however, chicken curry will become spicy. No? That's how you make a curry thick and thin. No? You put a lot of water, curry is very thin, you can't eat it. Chicken curry is like rasam now. If you want to make the curry thick, you heat it, evaporate the water. When you evaporate the water, it becomes thick. Same logic here. They are telling already it is 5%. They wanted to bring it to 10%. That means they wanted to increase the amount of acetic acid. One method, you put acetic acid. Second method, you remove water. Now, here they are asking a method. What they are asking? Name a technique that can be used to obtain a solution that contain about 10% acid by mass using a sample of vinegar. So you already, they have given a sample of vinegar. They wanted to do this. What you can do? They have talked about the boiling point. Now, what method they are talking about? Adding acetic acid, then nothing evaporating water.
Evaporating water.
Evaporating water.
And why they are telling acetic acid's boiling point is 118? Why they should tell that specifically?
Because it doesn't evaporate.
Anhar. Tell me, what's the boiling point of water?
100 degrees Celsius.
100 degrees.
And acetic acid, the less than acetic acid.
Less than acetic acid.
So if I heat this, who will vaporize first? Acetic acid, the water.
Water.
That is what we need to do. By heating, I need to remove water. Just imagine if this one is 18 K, just imagine. If the boiling point of acetic acid is 18 K, just imagine hypothetical situation. It's 18 K, when you heat it, who will vaporize first?
Acetic acid.
Acetic acid.
The concentration will increase the decrease.
Decrease.
We don't want that. We don't want that. That's why they are telling exactly this. So the technique is what? Vaporization or evaporation. You don't write evaporation. Actually, there's a difference between vaporization and evaporation. Write vaporization. Vaporization. Or you can tell heating the solution, boiling the solution, anything that brings the meaning as vaporization is correct. That's a technique. Understood. Adi, tell me yes or no. Understood?
Yes, sir.
Yes, sir.
Now what is done? What is not done? 2020 has to be done. 2020 with the right need. 18 done. 19 done.
22.
22 also has to be done. What shall we go first? Shall we finish 2020?
Okay.
Okay, sir.
Okay, sir.
This also needs a bit of hydrocarbon lesson. It's an interconnected thing with hydrocarbon. Sorry, we'll go. A longitudinal section of a fractionating tower used for refining crude oil is given below. Containing abundance are compound X in fraction release from outlet 1. From 1 X is coming. Compound Y in the fraction release from outlet 4. And compound Z in fraction release from outlet 6. Right. From top X is coming. From middle Y is coming. From bottom Z is coming. But you should understand from that why they are specifically talking about that. Top, middle, bottom. But you should understand. This is how a fractionating tower works. It has several volatile components. No, I will take A, B, C volatile components. Let's take boiling point of A is 60 degrees Celsius. Boiling point of B is 100 degrees Celsius. Boiling point of C is 200 degrees Celsius. When I supply heat, supply heat means at once you don't supply high amount of heat. You supply low heat, gradually increase, and first, who is going to come out? Who is going to vaporize? Who is going to get boiled?
Boiling point of A.
First is guaranteed A. A has 16. You're supplying heat from the lowest value, 10 degrees, 20 degrees, 30, 40, 50, 60. When first 2 is going to vaporize A. The component that vaporizes first comes out from the topmost chamber. I taught this logic in the theory class. The component that vaporizes first will come from the topmost chamber. So from top, A will come. You wait until all the A vaporizes and finishes. Once when it finishes, nothing will come here. Then you know all they have come. All A are released now. Then you again increase the temperature, 70, 80, 90, 100. At 100 now, who is going to vaporize? Second?
B.
The component that vaporizes second will come from the next chamber. You wait until all the B comes out. After all the B comes out, what do you do?
Increasing the temperature.
Remaining C is there.
No need to raise Puta. A is gone, B is gone. What is going to remain? C is going to remain. In my setup, C will remain. If there are a lot of other components, I think others will remain. Then you have to heat up and bring C out. So logic is, remember, the one that has the lowest boiling point will vaporize first and come out from the first chamber, top chamber. The one that has the highest boiling point will come at the end in the lowermost chamber. Now tell me XYZ, who has the lowest boiling point?
X.
X's boiling point is the lowest. Highest boiling point?
Z.
And Y has an average boiling point. What are they asking? Roman 1. By what common name is the group of organic compound contained in abundance in crude oil known? If you are not written answer, don't panic. It is hydrocarbon lesson. Answer is hydrocarbon. Don't worry on this. Don't worry on this till you have not done this lesson. Answer is hydrocarbon. Just write it and key. Don't panic if you are wrong. Don't worry. It's a simple lesson. Surely you will get the marks here. That's why they have put it as the first question. Very simple question. If you are not answered, don't worry. You have the marks for this. Roman 2. Name the crude oil refining technique employed in the Tavan. This one. This is mixtures lesson. What's the technique?
Fractional distillation.
Fractional distillation.
Roman 3. Name the boiling point of compound X, Y, Z are Tx, Ty, and Tz respectively. Write them in ascending order. Ascending order is lowest to the highest. Who has the lowest?
X.
So ascending order, Tx comes first. Tx comes first. Tx. Second is, who has the average boiling point?
Y.
Y has the average one. Highest is Z. Highest is Tc. That's the ascending order. Tx, Ty, Tc. Roman 4. X is a compound with a single carbon atom, contains carbon and hydrogen only. X is a compound with, it's also hydrocarbon, but using your bonding lesson, you can answer that. That's why I kept it there. You can answer this. X is a compound with single carbon. One carbon is there. And contain carbon and hydrogen only. Tell me, using your bonding lesson knowledge, what compound has one single carbon and hydrogen? What's the compound? Not one carbon. They are telling one carbon. They are not telling the number of hydrogen. You should know the number of hydrogen. One carbon and a certain number of hydrogen. What is that?
Methane.
They are talking about methane. Methane. What's the formula of methane?
CH4. CH4.
What's the Lewis structure of methane? One carbon. How many hydrogen are there?
4.
That is the Lewis structure of methane. What are they asking? X is a compound with single carbon and hydrogen only. See, they are telling single carbon, hydrogen. They are not telling the number because there are 4 hydrogen. Draw the dot and cross diagram of X molecule. If you write this and come, will you get the marks?
No.
It is not dot and cross. This is Lewis structure. They are asking dot and cross. Convert it into dot and cross. What you do? X, 4 hydrogen are there. X is carbon. Sorry, X is methane. C is carbon. So 4 hydrogen are there. One bond contains how many electrons?
2 electrons.
2 electrons. So I have to mark 2 electrons. In dot and cross diagram, how you mark the electron? If you use cross for carbon, you can use dot for hydrogen. Here also, one bond, 2 electrons are there. Cross for carbon, dot for hydrogen. Here also, 2 electrons, dot, sorry, cross for carbon, dot for hydrogen. 2 electron, cross. That is your Lewis dot and cross for methane. This is your answer, right? Not this. Sorry. Roman 5, write the balanced chemical equation relevant to the complete combustion of 1 mole of compound X in oxygen gas. Again, hydrocarbon lesson required. I will write the equation, just write it and keep. What are they telling? Balanced chemical equation relevant to the complete combustion of 1 mole of compound X in oxygen gas. Now, what is X? What is X? Methane. X is methane. They are asking you to write the balanced chemical equation for the complete combustion of methane. During combustion, what happens? That you know. During combustion, what happens? A combustible substance reacts with oxygen. A combustion of magnesium. What is combustion of magnesium? Magnesium reacting with oxygen. You're combusting a paper. What does that mean? A paper is reacting with oxygen. Combustion of petrol. What is combustion of petrol? Petrol reacting with oxygen. So combustion of methane. Methane is reacting with oxygen. Remember, when methane reacts with oxygen, methane is actually called as a hydrocarbon because there is carbon and hydrogen in it. It's a hydrocarbon. Remember, when a hydrocarbon is combusted, 2 products are formed. 1, carbon dioxide, and 2, water. During complete combustion of a hydrocarbon, carbon and hydrogen containing compound, 2 products are formed, carbon dioxide and water. This is a basic logic in hydrocarbon. Simple logic. No? This is hydrocarbon. When it is combusted, when it reacts with oxygen, 2 products, carbon dioxide and water. Now, if you take petrol, petrol contains octane, C8, H18. Tell me now, if they ask you in the exam, write the complete combustion of octane. How do you write? Now, this one you will understand how to write the formula. For now, don't worry about the formula. How do you write the complete combustion? Plus
Oxygen.
oxygen. Arrow. What are the 2 products?
Carbon dioxide.
Nice. Remember, any hydrocarbon, this is a carbon and hydrogen containing compound. It's hydrocarbon. Any hydrocarbon, when you combust it, that means when you react it with oxygen, 2 products are formed, carbon dioxide and water. Later, we'll be learning this. But as the question is coming, I just gave you the idea. That's the complete combustion. Now balance it. 1 carbon, no problem. 4 hydrogen. How many hydrogen are here? 2. This side 4, this side 2. So what's the number I should put in front?
2.
1 carbon, no problem. 4 hydrogen, 2 into 2, 4 hydrogen. That also no problem. Now count the number of oxygen. 2 oxygen, 2 into 2, 2 into 1, 2 oxygen. 2 plus 2, how many oxygen? 4 oxygen. Here 2, 4 oxygen. So here in front, what's the number I should put?
2.
2 into 2, 4. 2 plus 2. That's your balanced chemical equation. Write it in. Right. Roman 6. The substance released from outlet 7 of the tower is used to construct road. 7. What is that? What is going to be the end product during fractionalization of road oil? Name that substance. That's star. Or anything. That is what is used to make roads. Roman 7. State an environmental problem caused by the gaseous compound that would be released to the environment during refining of crude oil. Now, during refining crude oil, there can be carbon dioxide, sulfur dioxide, carbon monoxide like gases released. You actually need biosphere lesson to answer this, but using your general knowledge, tell me carbon dioxide, sulfur dioxide, carbon monoxide like gases will do what to the environment?
Pollution.
Air pollution.
One answer. Good, one answer.
Air
Any other?
pollution.
Respiratory.
The ozone layer.
Global warming.
Global
The carbon
warming.
level will be unbalanced.
Carbon dioxide level will be unbalanced. So I'll write global warming. Air pollution correct, global warming correct, carbon dioxide level will be unbalanced correct. Hurry. Now what's the question remaining for us? 2022, no? That is from salt extraction. Extraction of common salt, sodium chloride, from seawater is a chemical industry carried out in Sri Lanka. State 2 environmental factors that should be present in a location suitable to install a salton. What are the environmental factors you should consider before you construct a salton?
Coastal area.
Minimum amount of area.
Minimum amount of rainfall.
Y'all don't unmute. No. Salton should be closer to a coastal area. 1. There should be a flat land. 3.
Minimum.
Clay soil with minimum percolation of water. Those are the main environmental factors. What are the climatic factors you need to consider? Less rainfall, minimum annual rainfall.
Climatic conditions.
There should be what you call strong sunlight, strong wind should be
Windy.
there. Wind should be strong. Those are things. High temperature. Those are the climatic factors. Yeah, they're only asking environmental factors. So you can write even climatic factors, you can write under environmental factor. It don't get much separated. So if you're not ready to write down, I'll tell you. Salton should be closer to the coastal region. Salton should be closer to the coastal region. Salton should be closer to the coastal region. Second, there should be flat land. There should be flat land. There should be flat land. Roman 2. Name the 2 separating techniques related to the extraction of salt from seawater. Today at the beginning we talked about it. Extraction of salt. What are the 2 separation techniques? Evaporation, crystallization. Evaporation, crystallization. For now, if you are written vaporization, okay, you can take marks, but vaporization is not correct. Properly write it evaporation. Later in the heat lesson, we'll be discussing what is vaporization, what is evaporation, what is boiling, all those things. The correct way of writing it is evaporation and crystallization. Evaporation, crystallization. Roman 3. Salt taken out. Salt taken out from salton is heaped as prismatic piles and kept for about 6 months. What is the reason for this?
Self-dissolving.
To reduce the water content in salt.
I'll ask a question like this. There are 3 tanks used in salt extraction. What is precipitated in the 3rd tank? Pingala should come. First tank, calcium carbonate precipitate. Second tank, calcium sulfate precipitate. Third tank, magnesium chloride plus magnesium sulfate. And our main hero, who is the hero? Sodium chloride will precipitate. Repeat with me. First tank, calcium carbonate. Second tank, calcium sulfate. Third tank, magnesium chloride, magnesium sulfate with sodium chloride. I taught you all a small rhyme to memorize this. Kaka comes first, Kasa comes second, my God comes third. Why Kaka comes first? Calcium carbonate. Calcium carbonate. Ka comes first. Second is Kasa. Why Kasa? Calcium sulfate. Calcium sulfate. Kasa. Third, why my God? My Mg. Mg is coming third. What is Mg? Magnesium. What are the magnesium things? Magnesium chloride, magnesium sulfate. And of course, the main hero will come in the third tank. So Kaka comes first, calcium carbonate. Kasa comes second, calcium sulfate. My God, Mg, magnesium chloride, magnesium sulfate, and the main person, sodium chloride. So calcium carbonate first tank, calcium sulfate second tank, magnesium chloride, magnesium sulfate together with sodium chloride is the third tank. I'm talking about third tank. So magnesium chloride, magnesium sulfate, and sodium chloride comes. That is coming in the third tank. From this, you have to separate the sodium chloride and take it out. How do you separate the sodium chloride and take it out? You collect this precipitate and form it into piles, small mountains in a separate place and keep it. These piles are called prismatic pile. This is taken, heaped into prismatic piles. What is there in prismatic pile? Magnesium chloride, magnesium sulfate, sodium chloride. Usually this is kept for about 6-month time period. During 6-month time period, what will happen? Magnesium chloride, magnesium sulfate has a special ability that sodium chloride doesn't.
They will absorb the moisture in the atmosphere.
They will
Magnesium chloride and magnesium sulfate can absorb the moisture. Absorb the moisture from the atmosphere. There is a proper word for that. Ability to absorb moisture. What is that called as? What's the word? Who can remember the word?
hygroscope.
Hygroscope. Magnesium chloride, magnesium sulfate can absorb moisture. That ability is called hygroscopic nature. So magnesium chloride and magnesium sulfate are hygroscopic. They can absorb the moisture. Can sodium chloride absorb moisture? Is it hygroscopic?
No.
Nahi beta. It doesn't absorb moisture. Now, once when magnesium chloride and magnesium sulfate absorb the moisture, what is moisture? Water. When it absorbs water, it will remain as solid or it will turn into a liquid. When it absorbs moisture, it will remain as solid or turn into liquid.
Liquid. Turn into liquid.
This absorbing moisture and turning into a liquid, there is a special word you give for that ability. What is that ability called as? Deliquescent. Ability to absorb moisture is hygroscopic. Due to absorption of moisture, turning into a liquid is deliquescent. Ability to absorb moisture is hygroscopic. These are done in the theory class. Ability to absorb moisture is hygroscopic. Due to absorption of moisture, turning into a liquid is deliquescent. So remember, magnesium chloride and magnesium sulfate both are hygroscopic and deliquescent. They can absorb moisture, turn into a liquid. Sodium chloride is not hygroscopic. It doesn't absorb moisture, not deliquescent, can't turn into a liquid. So when you keep it like this for about 6 months, what will happen? Magnesium chloride and magnesium sulfate will absorb the moisture, turn into a liquid. If it turns into a liquid, it will surely go. Sodium chloride is not hygroscopic, not deliquescent. It won't absorb moisture. It won't turn into a liquid. Then it is going to remain. So after 6 months, all magnesium chloride, magnesium sulfate will go. Sodium chloride will remain. What's the question asking? Salt taken from the solvent is heaped as prismatic piles and kept for about 6 months. What is the reason for this? What's the reason for this? During 6 months, magnesium chloride, magnesium sulfate will absorb the moisture, turn into a liquid and go, leaving only sodium chloride. If you are not written, write down. During 6 month time period, During 6-month time period. During 6-month time period. Magnesium chloride and magnesium sulfate. Magnesium chloride and magnesium sulfate. Magnesium chloride and magnesium sulfate. Absorbs the moisture. Absorbs the moisture. And turn into liquid. And turn into liquid. And turn it liquid. Leaving only sodium chloride. Leaving only sodium chloride. Roman 4. Some countries in the world obtain drinking water by simple distillation of seawater. Draw a label sketch of an apparatus suitable to demonstrate that separating technique in the school lab. Draw a label sketch. They're asking you to draw a sketch to show how countries in the world obtain drinking water by simple distillation. Simple distillation setup you have to draw. Nothing big. Anybody can draw that and get the marks. So if I draw it, that's your round bottom flask. See that you well seal it. There should be a pressure regulatable tube inside. That's the Liebig condenser. I'm just roughly drawing. Now y'all, I know y'all are better artists than me. You can draw well. This is the Liebig condenser. That's the tripod. Maybe that you can use it as a Bunsen burner. So if I label them, see that you're labeled. If you're not labeled, no marks. Inside this, you have the seawater. That's the round bottom flask. Delivery tube. Liebig condenser. Tell me, in a Liebig condenser, you have to circulate water. Where do you send the water in?
At
From
the end.
bottom the top.
At the
In
bottom.
is given from where?
Bottom.
Properly mark that. Water in. Out from here. Water out. And here you will have distilled water coming. You keep something like a beaker to collect. This is the tripod. This is the that is the Bunsen burner. Beaker. This is a proper label sketch. If you're just drawn, 0 marks. Not labeled, 0 marks. See that you label. Labeling is very important in science. If you're not drawn, take a screenshot. Is there any questions left? 24 done, 22 done, 21 done, 20
No, sir.
done, 19 done, 18 done. 23 and 22 I didn't do. That you all can take and do. 23 and 22 you can take and do. Horine. That's the plan for today. That's the plan for today. I hope you all understood now how to apply the theory that you learned in the paper. Do those two papers as well. If you can, go backwards until about 2016. Don't go below 2016. First finish the papers up to 2016 because that is our new syllabus. Up to 2015, you can go backwards, try by your own and finish off all these questions. There is a plan in doing waves lesson question discussion as well, and then geometrical optics lesson question discussion as well. I will update in the groups when it is going to fall. See that you all follow the group or follow the channel somewhere, get the updates. Of course, to the normal theory students, I tell in the classes as well. So from there, you will get the update of those things. All right. Any questions related to our discussion today? Now you can raise. Now don't ask me, sir, fully explain what is this, what is that. That's a full theory section. Anything related to today's section? What's the definition of concentration? The amount of solute present in a given volume of solvent is concentration. The amount of solute present in a given volume of solvent. How much of solute is there in a given volume of solvent? Oh, now if I tell 2 mole per decimeter cube, 2 mole per decimeter cube. What do you mean by 2 mole per decimeter cube? In 1 decimeter cube, there is 2 moles of substance. In 1 decimeter cube, there is 2 moles of a certain substance. So the amount of a certain substance, that is usually the solute, present in a given solvent. What is saturated solution? A solution that has reached the maximum concentration. A solution that has reached the maximum concentration. For a solution, there will be a maximum concentration it can reach. Now, for example, let's take you are dissolving sugar in water. There is a maximum amount of sugar you can put in water and fully dissolve. When you dissolve maximum amount of sugar and dissolve it, that is a saturated solution. It has reached the maximum concentration. Horric. What we are doing in solvent extraction to obtain the solvent without, I couldn't read it. What we are doing in solvent extraction is when there is a solute that is slightly miscible in one solvent, but very well miscible in another solvent. From that slightly miscible solvent, we extract it to the very well visible solvent. Like that, when you do several times, you get a certain amount of considerable solute into that miscible solvent. Then you take it out, vaporize the solvent, you have a certain amount of considerable solute in it. Why are we sending water from bottom? Why are we sending water from bottom? Because the bottom has to be cool compared to the top. Because whatever the vapor that is coming from here, its final exit is from the bottom. So before it comes out from the bottom, it has to somehow be condensed. To somehow condense this, maximum coolness should be given from the bottom. So if you supply maximum cool from the bottom, somehow the vapor will be turned into its liquid. Now just imagine if the bottom is not cool, if the bottom is not cool, if the bottom is hot, if the bottom is hot, will all the vapor be turned into a liquid? There is possibility that again vapor can come out. So to maintain the turning of vapor into liquid, bottom has to be cool. Bottom has to be maintained cool. Bottom has to be more cooler. Bottom has to be more cool. So to maintain the bottom cooler, we supply the water in from bottom. So whatever the water that is coming in will be however cooled. Water that is coming in will be however cool. So however the vapor will be turned into the liquid. Now if you send water in from here, this part will be cool. This part will be comparatively hot. I don't tell it will be very hot. Comparatively, this part will be hot because water is circulating and coming out. So already it has circulated, water has absorbed the heat, it will be hot. The water that is coming out will be hot. So bottom will be hot compared to the top. So there is a possibility that vapor that is entering from here due to the heat here again turns into a vapor. We don't want that to happen. So bottom has to be cool. So to maintain the bottom cool, only we send the water in from bottom. Hurry. Hurry. Hurry, right. I will finish from there. Keep working hard. I will update you all in the groups and the channel. When is the next discussion? Most probably it will be the waves lesson. So I'll update you all when is waves lesson discussion. Okay. Okay then. Thank you. Good night. Still day is not finished. Keep working. Finish off some more questions. You can download some papers and do some more papers, some more questions, and finish off the day in the best way. Good night. Bye.
Bye.
Bye, sir.
Bye.
Thank you, sir.
Bye, sir.